Now, Conklin's a pretty smart fella, so he's probably going to realize that if he goes walking speed, that then Shuyu would probably have to sprint, right? So Conklin's going to do his thing. Ready, set, go. Here you go.
Are you not faster?
Look at that. Okay, go one complete revolution. And stop. Okay, go and keep it there. So guys, they had an angular displacement of what? Angular displacement of 2 pi radians. They made one revolution, that's equal to an angular displacement of 2 pi radians. It took them 10 seconds, so we would take 2 pi radians divided by 10 seconds, which would be what, 6.28 divided by 10, and we get 0.628 radians per second as our angular what? Angular velocity. You guys with me there? You guys seeing that? Okay, now, here's what we're going to try to do. I want you to speed up, and I want you to have an angular acceleration that is constant, and I would like you to have Shuyu running by the time she gets back to here. And I want to have constant angular acceleration. Do you think we can pull this off? Okay, ready, set, go. Walk, 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 faster, 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 faster. Faster, 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 faster. Okay, stop. Okay? Now, guys, you actually seeing that is pretty important, okay? The angular displacement was still what? 2 pi radians. The angular velocity was changing the whole time, which meant that they had an angular acceleration. Okay? Now, just for the sake of this experiment, in order to make that happen, did there have to be a centripetal force? Did Shuyu have to hold on? Because if she didn't, if she let go, she would continue doing what she's doing. She would have made this first lock right into the case. But you guys understand that piece. Okay? Now, I think seeing it and hearing the terminology is pretty important, because when we start putting omegas and alphas, it kind of tweaks your brain a little bit. So angular displacement, you have to feel what that is. It's just basically the distance you've traveled in a circle. And it's kind of interesting. She had an angular displacement of 2 pi. He had an angular displacement of 2 pi, even though he didn't travel as far. Okay? Now, when we start talking about the terminology, we're going to also talk about something called tangential velocity, which is how fast you're going actually tangentially. So if we were to break that arm bond, how fast she would go flying off in that direction. Okay? Now, we all know that they all have the same angular velocity, but do they have the same tangential velocity? And you guys know this because you saw Conklin was walking about like this, and Shuyu was out there running at top speed. Does that kind of make sense? Okay, guys, we're going to talk about rotational kinematics today, which is basically taking everything we've learned in a linear fashion and putting it into circular motion, okay? Or spinning objects. So you'll notice I say rotational kinematics for spinning objects. And guys, some of the vocab we've already talked about a little bit is going to be S, which is the arc length, okay? Which is the physical distance that you're actually traveling in meters. The angular displacement, which is going to be the radians or the degree type displacement. We won't measure it in degrees anymore. We're going to be talking about radians. We have the radius, which you guys know what that is. This term, omega, is the average angular velocity. And that, guys, is going to be equal to your displacement divided by time, just like it was in a linear sense. And then we have angular acceleration, which is your change in angular velocity, all over change in time. And guys, these are just the symbols, one to make you aware. They look an awful lot alike. That looks like a V, but it's a little bit of a W. It's called the omega. And then that's alpha for angular acceleration. Okay? Now, you guys all, we did a survey. You said most of you guys understand what a unit circle is. It's a circle with a radius of 1. And if we go around that circle, okay, that's going to be our distance traveled or our arc length. And then the angular component we're going to measure in radians. So as a review, there's 360 degrees in a circle, which equals 2 pi radians. Okay? So if we divide 360 by 2 pi, we come up with 1 radian is about the same as 57.296 degrees. Okay? So, and then guys, the definition of angular displacement, this is a formula that you want to know. Angular displacement is designated by theta, is going to be equal to your arc length, or the distance that you've traveled on the circle that you're traveling, divided by the radius of that circle. Okay? Now, it's kind of weird, guys, because S is in meters, R is in meters. So if you take meters divided by meters, what is your unit? There's really no unit, but we give it a unit called a radian, even though meters divided by meters is basically cancels each other out. Okay? So later on, we're going to talk more about that. We're going to multiply some things. You're like, where'd the radians go? Well, they're not really there in the first place. Okay? Now, guys, this is so simple. I've already talked about it, but I'm going to hit it again. Angular velocity, which is omega, okay, is equal to the change in your angular displacement, okay, over change in time. And just to do an example of this, I said if a fan is rotating at 300 revolutions per minute, what is its angular velocity? Well, guys, if you look here, the displacement is 300 revolutions. And this is a good point here. A revolution is equal to 2 pi radians. So you'll see that I've converted it into 1884.96 radians. And then a minute is 60 seconds. So if you take those and you divide them, you come up with an angular velocity of 31.416 radians per second. Okay? So if that fan blade is going 300 RPM, that's your angular velocity in radians per second. Now the only thing that, it's easily conceptually, it's just hard to visualize what 31.4 radians per second is in your brain. If you work with this enough, you'll kind of start to pick up on that. Okay. I guess if you think, what's 300 revolutions per minute? Okay. Well, if you went around once every second, that would be 60 revolutions. So that's what, about 4.5 times that many? Okay, so that kind of gives you a feel on how fast that thing's rotating. Okay? Now, guys, if we come over here and we look at angular acceleration, that's how fast your angular velocity is changing with time. So a real simple equation. And I did an example. I said a fan goes from rest to 340 radians per second in 4 seconds. Determine its average angular acceleration. Okay? Well, guys, this is pretty straightforward. Change in angular velocity final was 340 minus initial was 0, all over 4 seconds. We get a radians per second. We get 85 radians per second squared as your angular acceleration. Okay. Now, a question was asked when we came back from our little demo. If you go all the way around the circle, is your displacement 0? No, because we're just going to continue to add those as we go. The only way you get negative displacement is if you do what? Go the other direction around the circle. Okay? Now, how do I say this? Well, we're going to talk more about it later. If you're going clockwise around the circle, we usually treat that as negative. If you're going counterclockwise around the circle, we treat that as positive. And we'll hit that a few more times, so don't worry about that right now. Okay? Now, guys, just like when we did linear stuff, if we get to a point where we have constant acceleration, then we can start to apply basically the kinematic equations. Okay? So let's look at these kinematic equations. Let's bounce over here really quickly. Guys, if we're comparing the linear and angular variables, okay, and if we're looking at displacement, linear, we're changing x, we got change in theta. Velocity, we're changing x over change in time. Angular, we're going to be delta theta over delta time. Acceleration, delta v over delta t. That's easy stuff. Here it's going to be delta omega over delta t. Guys, there are those total direct correlations. Okay? Then if we come down to the kinematic equations, guys, we can apply those in the same way. And these, you've seen these 100,000 times. So V equals V naught plus AT. You can see, guys, is going to be omega minus omega naught plus alpha t. Okay. So we can use the kinematic equations in a circular spinning rotational context, and I think you'll see how the variables correlate, right? Pretty simple. So let's do a quick example problem. I said if angular acceleration is constant. Now that is huge, and I'm going to underline it in pink like 3 times, because when is the only time we can use kinematic equations? When we are accelerating at a constant rate. Okay? It says we could use kinematic equations to solve the problems. Example, if the wheel is accelerating angularly at a rate of 2.2 radians per second squared from rest, what will its angular velocity be after 5 seconds? And what will its angular displacement, what is its angular displacement after 5 seconds? So let's grab this. We'll use it as a demo. Here's our wheel. We are going to put some sort of torque on this wheel to get it to accelerate. Okay? So basically what we're going to do is I'm going to put a force on it, and the force, I'm going to make it not very big so you can see it right now. But if I put a consistent force on it, what does the wheel start to do? It starts to accelerate, right? Does that make sense? It's saying its acceleration is 2.2 radians per second squared. So if we come in, what will its angular velocity be after 5 seconds? We know its angular velocity at the beginning is 0. We know the time is 5 seconds. We know the angular acceleration is 2.2. So we are going to find angular velocity for A. So we just plug it into the kinematic equation that is appropriate. And we solve, and we get an angular velocity of 11 radians per second at the end of the 5-second acceleration. Make sense? Okay. And then, guys, if we go to B, what is the angular displacement after 5 seconds? We're looking for the theta here instead of the omega. So we plug it into the appropriate kinematic equation. And we have 1/2 2.2 times 5 squared. We come up with an angular displacement of 27.5 radians. Okay. So guys, just to summarize, the only things that are difficult is for kids to get the terminology down, I think. How far you go around in the spinning is called the angular displacement. If you divide that by the time it takes, you get your angular velocity. And then if you divide how fast your velocity is changing by time, then you get your angular acceleration.